could do without the observer.
The physics data tells us that an object itself is really a simplification for what we call out there. One is particularly when we're looking at atomic and subatomic particles or atomic and subatomic matter in any form. What we find is how we go to look at it, what we choose to examine it with, actually changes the properties of what we observe to be out there.
Is this the observer, and which is so intricate to understanding the wacky, weird world of quantum particles and how they react? Is this, then, the observer? And even though we cannot have a quantum field without the observation of scientists who have gone there, who have uncovered it, layer after layer after layer, they're all observers. But not one of them agree conclusively on all points in the field, because they are perceiving the field mathematically from different angles of perception.
We don't know in quantum mechanics how to hook ourselves as observers up with the world. We don't know how to treat ourselves as observers as just another part of the physical system that we're describing. The only way we know how to do quantum mechanics as it's traditionally formulated is to keep the observer outside of the system you're describing. The minute you put him in, you get all these paradoxes. And we're forced to say things in quantum mechanics like, look, the book is doing what it's doing because of quantum mechanics, and I see that because I'm there and I see it, and you better not try to analyze that second part of the sentence in terms of applying quantum mechanics to it, because it's going to break down. That's why there are these two separate laws of the evolutions of physical systems. One that applies when you're not looking at them, the other that applies when you are. But that's crazy.
There's no way that we're ever going to mathematize or put into mathematical formula this very act in which a conscious observer comes up with the answer. People say, oh, the measuring instruments, the recorder records it, and there it is, it's on the tape, it's recorded. You forgot one part of the equation. Somebody has to look at the tape. And until somebody looks at the tape, it ain't recorded at all.
When you are not looking, there are waves of possibility. When you are looking, then there are particles of experience.
A particle, which we think of as a solid thing, really exists in a so-called superposition, a spread out wave of possible locations. And it's in all of those at once. The instant you check on it, it snaps into just one of those possible positions.
It's easy to generate situations where the equations of motion will predict that, say, the wave function, the psi of a certain basketball, is uniformly distributed all over the basketball court. We don't have any idea what a state like that would look like. According to the law of quantum mechanics, that's supposed to be a state in which it fails to make any sense even to ask the question, where is the basketball? That is, according to the law of quantum mechanics, asking the question, where is a basketball whose psi is uniformly distributed over a whole basketball court, is the logical equivalent of asking about, say, the marital status of the number 5. Okay? It's not that you don't know the answer, you don't happen to know whether the number 5 is married or a bachelor. It's that the question somehow is radically inappropriate in the first place. The number 5 doesn't have a marital status. There's nothing there to ask about. And similarly, a basketball whose wave function was uniformly distributed over the entire basketball court would not have a position that could even coherently be asked about. Now, the crux of the measurement problem is precisely that, although the Schrödinger equation predicts under certain circumstances which we basically know how to reproduce in the laboratory, that basketballs should go into states like that, states where there fails to be any intelligible fact, any sensible question even about where they are. And yet, when we go look at the basketball court in situations like that, we invariably see either a basketball over here or a basketball over there, or a basketball over there. The fact that we see the basketball in some specific location, as opposed to seeing it in some science fiction state that we can't even imagine what it looks like, where there fails to be a question about what its location is. The fact that we always see it in some definite location is an explicit violation of these equations of motion, and it's exactly there that the measurement problem comes up.
When you observe, things happen. When you don't, they don't.
Superheroes use superposition, with the world being potential strips of reality, until we choose. Heroes choose what they want, being in many places at once, experiencing many possibilities all at once, and then collapsing on the one. The question is, how far down the rabbit hole do you want to go?
Your own mind is creating multiple possibilities in your subconscious. The superpositions of possibilities are in your subconscious. I mean, you may be consciously aware of them, but they exist, I think, in superposition of multiple possibilities, which after a while will collapse to one or the other.
Project or plan into the future or cast a thought ahead of itself.
Nice shot.
But the great-great-granddaddy of wacky quantum weirdness is entanglement. If time reversal symmetry destroys the notion of time, then entanglement crushes our experience of space. Two objects, two electrons created together, are entangled. Send one to the other side of the universe. Now, do something to one, and the other responds instantly. Instantly. So, either information is traveling infinitely fast, or, in reality, they are still connected. They are entangled. And since everything was entangled at the moment of the Big Bang, that means everything is still touching. Space is just the construct that gives the illusion that there are separate objects. Are we far enough down the rabbit hole yet?
You now can see in numerous labs around the United States objects that are large enough to be seen by the naked eye, and they are in two places simultaneously. And you can actually take a photograph of that. Now, I suppose if you showed a photograph, they'd say, oh, great, here's this nice blob of colored light, and I see there's a bit of it over here and another bit of it. So you got a picture of two dots. What's the big deal? Superposition is pre-detection. What I was speaking about in the film is post-detection. Now, under normal circumstances, a single object, once it has been detected, is in just one position. However, there are states of matter that have been created now in which objects can be in multiple positions simultaneously, not just two, but actually as many as 3,000 positions. The first of these objects were called Bose-Einstein condensates. And they are single wave functions, meaning they are single particles. But even though they're a single wave function, the wave function has multiple positions. And if you say, well, look right in the chamber. You can see it right there. Oh, I see two things there. You say, no, that's not two things. That's one thing. It's the same thing in two places. Tricky point here is that it's still a single wave function. It's not 3,000 separate wave functions. It's one wave function. So it's one particle. I'm not sure that people's jaw would drop about it because I don't think people really believe it. And I don't mean that people say, oh, you're lying, or, oh, the scientists are confused. I think it is so mysterious that you can't even understand how amazing it is. One particle in 3,000 different locations.
Now, if you were to weigh one of them, would it weigh 1/3000th?
Well, you can't weigh one of them.
Why?
Because it's one particle. It's one indivisible particle.
But if it's in different locations, can't you put a scale under one?